I'm going to start now.
Okay, yeah.
Okay. So Mike Midledge and myself, Guillaume Hachem, are going to present to you the following topic, battery technologies for PHEVs. So our presentation will consist of 6 parts, including the conclusion, starting with an overall explanation of plug-in hybrid electric vehicles, then introducing and comparing the different battery types found in these vehicles. And the third part will focus on the different battery chemistries for lithium-ion batteries. Part 4 will be about the socioeconomic and environmental aspects of PHEVs. And finally, we will discuss the future battery technologies for this type of vehicles. So, as I mentioned earlier, I'm going to start with an overview of PHEVs. This part will include a general explanation of their functioning, the different components found in these vehicles, and the different components configuration. Now, what's a PHEV? First, as its name implies, plug-in hybrid electric vehicles rely on the use of 2 energy sources, fuel such as gasoline, or diesel to power the internal combustion engine, and electricity coming from the traction battery pack to run an electric traction motor. The batteries can store very large amounts of energy and are charged with an external power supply, but also with the work of the internal combustion engine and with a process called regenerative braking. And these 2 will be discussed later in the presentation. Now, what distinguishes this type of vehicle from this typical hybrid car is the capacity of the battery pack. So PHEVs have the ability to store higher amounts of energy thanks to a way larger battery pack, which gives them the ability to operate on full electric for moderate distances. And note that the maximum allowable distance on fully electric is known as the electric range of the car, and it ranges from 15 to 60 plus miles for the newest models. Sorry, can you go back, Mark? Now, although all PHEVs rely on 2 types of energy sources, we have to distinguish between light-duty and heavy-duty PHEVs that have different modes of operation. And for light-duty PHEVs, when the battery becomes mostly depleted of its stored energy, or when the user drives at higher speeds, at highway, for example, the combustion engine powered with fuel comes into action either to feed the battery or to provide the transmission with additional energy in order to rotate the wheels. So the combustion engine is also needed for air conditioning, of course. And for heavy-duty PHEVs, some use primarily the internal combustion engine in order to rotate the wheels, and the energy stored in the battery is mainly used to power only auxiliary equipment such as refrigeration units, compressors, etc., and to control the cab's temperature. Okay, so the major components found in PHEVs are as follows. First, there's the auxiliary battery that is used to launch the motor of the car before the traction battery pack is used. It also powers the car's accessories. The charge port is where you plug in the external power supply in order to charge the traction battery pack. The onboard charger is to convert the AC current coming from external power supplies to DC current, so it can be transferred to the battery pack. And the DC-DC converter converts the high voltage DC current from the traction battery pack into low voltage DC current in order to charge the auxiliary battery and to power the accessories. And the electric traction motor uses the current coming from the battery pack to rotate the wheels. And the power electronic controller is mainly the control unit system of the PHEV's whole electric compound. Okay, so there's also the electric generator, which is used to generate electricity through the process of regenerative braking. This technology is present in all types of electric vehicles, also in hybrid vehicles. And to explain it, when the driver removes his foot from the accelerator, the electric motor begins to spin in reverse to produce electricity, and the resulting energy is used to charge the vehicle's battery pack. So this reverse motion gives the feeling that the driver is manually activating the hydraulic brakes while removing his foot from the accelerator. However, this applied resistance is the effect of the regenerative braking. And the last component is obviously the exhaust system, where a three-way catalyst is used to catalyze the reaction converting primary pollutants such as VOCs, nitrogen oxides, and carbon monoxides to less polluting molecules such as water vapor, nitrogen, and there is also CO2 coming out from the catalyst. Now, there are different types of configuration used with PHEVs, allowing to switch from electricity to fuel or vice versa, or allowing to combine both energy sources. There is the series, the parallel, and the hybrid configuration. First, there is the series configuration, where the electric motor, the combustion engine, and the electric generator, and the battery are all connected in series. The engine is decoupled from the wheels, and its main function is to assist the electric motor when it needs more power. So the engine has a small power input and is also used to recharge the battery with fossil fuel. It's a fuel-efficient configuration, and the fuel tank can be reduced considerably because of less fuel use. And the capacity of the battery pack is the largest of all configurations. Here in the parallel configuration, unlike the series, the engine is coupled with the electric motor, and both are directly linked to the wheel's axle. Therefore, the electric motor operates alone at low speeds, and the engine operates alone at high speeds. And the figures show the mechanical coupling of the engine and the electric motor. The compound hybrid configuration is also known as the power split configuration. It's the most commonly used one because it combines the benefits provided by both the series and the parallel configuration. And this one combines and splits both power sources thanks to a planetary gear system. It's obviously the most fuel efficient alternative because power conversion losses are way less than those found in the series configuration. So let's dive right into the second part where we will present the different battery types found in PHEVs and compare them to finally explain their functioning. So the four types of batteries found in vehicles are lithium ion, nickel metal hydride, lead acid batteries, and ultra capacitors. Lithium ion batteries are the most common types of batteries because of its high specific energy, its low discharge rate, and its relatively good performance at high temperatures. And lithium-ion batteries are also used for cell phones and laptops. Nickel metal hydride batteries are mostly used in hybrid vehicles rather than fully electric vehicles because they have slightly less capacity compared to lithium ion. And they have longer lifespan than lithium ion and lead acid batteries. It's also interesting to note that studies have shown that they are tolerant to factors that exceed the normal operational limits, which is very desirable. And the last two are lead acid batteries and ultra capacitors that are usually used to add to other battery loads in electric vehicles. So these two are used as a secondary storage system. Of the mentioned battery types, the ultra capacitor is the only one that stores energy electrostatically rather than chemically, and they are usually used as car booster packs, power banks, etc. So in this comparative table, we can summarize the characteristics of each battery type. So for the cost, each battery type, the most expensive battery types are nickel metal and the ultra capacitors, and the lead acid batteries are quite cheap relatively, and lithium ion have moderate cost, and they're all energy efficient. And for the temperature performance for lithium ion, it ranges between -20 and 60 degrees. For nickel metal, it's between 28 to 54 degrees. For lead acid, it degrades above 25 degrees, and it also cannot operate at low temperature, as I said earlier. And the ultra capacitors, it's from -40 to 65 degrees. And the life cycle is shown also here. So for example, it's 5 years or less for nickel metal. And for lithium ion, it's only 2-3 years. So now we need to explain the difference between specific energy and the specific power in order to understand why lithium ion and nickel metal hydride batteries are used as primary storage system, whereas ultracapacitor and lead acid batteries are only used as secondary. So the specific energy is the total amount of energy an energy storage device can hold. Batteries have higher specific energy and can run therefore for much longer. And the specific power is the speed at which the power can be discharged. So ultracapacitors have far higher specific power, meaning they can provide a higher current. Can you go back, please? Thank you. It's therefore desirable for primary storage system to have high specific energy and for secondary batteries to have high specific power in order to instantaneously provide higher current when needed. So in this figure, we have the specific power at the y-axis and the specific energy at the x-axis. We can see that ultracapacitors have the largest specific power and the smaller specific energy out of all battery types. Lead acid batteries also have large specific power for small specific energy. And nickel metal hydride batteries have moderate specific energy and moderate to high specific power. And the lithium ion are the only batteries that can be found with both high specific energy and high specific power. And as we said, high specific energy means that the battery will run for much longer. This is why we decided to focus for the rest of our study on lithium ion batteries as a primary storage system for PHEVs. So before digging into the charging and the discharging of lithium ion batteries specifically, it would be great to explain how a battery works. So the two electrochemical cells found in a battery are used to transform chemical energy into electrical. Both a current and a voltage is produced within the system and power is generated. The positively charged cell is called the cathode and the negatively charged one is the anode. The electrical discharge is described by the flow of current from the cathode, which have higher electrical potential, to the anode. The flow of the electrons is always opposite to that of the current, which means that they flow from the anode to the cathode. And a separator isolates the cathode from the anode, and the electrolyte is the solution containing the ions where the chemical reactions take place, producing this flow of ions and electrons. And during discharge, cations are transferred to the cathode, where they combine with electrons, which themselves migrate from the anode to the cathode. In the third part, we are going to dig deeper into lithium-ion batteries, starting with its working principle. By charging the lithium-ion battery, electrons are being pushed from the cathode to the anode, which drives the positively charged lithium ions from the cathode to the anode by passing through the separator. The chemical reactions during the charging of a lithium ion battery are having a graphite anode with lithium iron phosphate interposed in the anode are shown in the slide. And you can see through the reaction at the cathode that Li plus ions are created at the cathode thanks to the flow of electrons induced by the charger. And at the anode, these ions combine with electrons after passing through the separator. And during discharge at the anode, lithium and graphite separate from each other and electrons flow through the load. And at the cathode, iron phosphate and lithium ions are converted to lithium iron phosphate. Now I will let the floor to Mark.
Okay, hello. Now we're going to talk about the types of lithium-ion batteries. Multiple lithium-ion batteries are currently available on the market with different cathode and anode chemistries. First, we have the lithium cobalt oxide, or LCO. As mentioned by its name, the cathode is made of cobalt oxide and the anode of graphite. It has been around for some time now and was used a lot in cell phones, tablets, laptops, and cameras. It has a specific energy of up to 200 watt-hour per kilogram. Later, during this presentation, I will compare the specific energies of the various battery types. It is to note that LCO batteries have a limited specific power, and that cobalt is expensive. This type is losing favor to lithium manganese, NMC, and NCA technologies, which we will talk about more later. Now we move on to lithium manganese oxide, or LMO. This battery type has been around since 1996. Its cathode is made of manganese oxide and the anode of graphite. It has been used in power tools, medical devices, and electrical powertrains. The specific energy of LMO is lower than LCO, but LCO is safer since thermal runaway is initiated at a much higher temperature. LMO is less relevant now since there is a limited growth potential for this type of chemistry. Another type of chemistry is the lithium nickel manganese cobalt oxide, or NMC. It was created in 2008 and was mainly used in e-bikes, medical devices, and EVs. Its cathode is made of nickel manganese cobalt oxide and anode of graphite. It has a high capacity of up to 220 watt-hour per kilogram and a high power. Its self-heating rate is low and it has a good performance overall. The NMC system is a leading system and its cathode chemistry is being more and more used nowadays. A fourth type is the lithium iron phosphate, or LFP. Commercialized in 1996, its long lifespan and good safety makes it a good fit primarily for energy storage. It has a low capacity compared to other lithium-ion batteries and is relatively expensive, costing $580 per kilowatt hour. The cathode is made of phosphate and the anode of graphite. Now moving on, there's the lithium nickel cobalt aluminum oxide battery, or NCA. This battery has been used by renowned EV manufacturers in their powertrains like Tesla due to its promising high specific energy and relatively low cost. However, its safety has been a concern due to the thermal runaway being initiated at temperatures as low as 150 degrees. A recent battery type is the lithium titanate. Created in 2008, it solved safety concerns for thermal runaway thanks to the wide temperature range it can operate in. It has a long lifespan with its cycle life ranging from 3,000 to 7,000 and has the ability to ultra-fast charge. This said, its low specific energy and high cost limits its applications. Now, the radar charts on screen summarize the performance of all these batteries relative to each other in terms of specific energy that's related to runtime, specific power, which is the ability to deliver high current, safety, performance at hot and cold temperature, lifespan, which reflects cycle life, and longevity and cost. The figure shown in this slide represents the specific energies of each battery type discussed previously. It shows how NCA allows for higher specific energy compared to the other systems. However, when comparing with the radar charts in the previous slide, it's important to note that LMO and LFP are clearly superior in terms of specific power and thermal stability. Additionally, even though LTO possesses the lowest specific energy, it has a higher lifespan than most other batteries and the best performance in cold weather. Now we'll discuss how these batteries can be physically implemented in the vehicles they power. So manufacturers have the option to arrange the cells either in a cylindrical, prismatic, or a pouch shape. Each of these shapes and form factors serve different needs. For example, the cylindrical arrangement is best for the mechanical strength of the battery as opposed to the pouch shape. Prismatic and pouch-shaped cells are better suited for delivering high specific energies. Now we will discuss the health and lifespan of these batteries. First, we need to define state of health, or SOH. It's a very important indicator of battery functionality that predicts how many times the battery can be charged and discharged before its end of life. In this part, we'll discuss the factors that affect the overall SOH of a battery, which are temperature as well as the charge-discharge rate and depth. We'll also present methods on how to try and extend the life of lithium-ion batteries. So first, performance of a lithium-ion battery can be heavily affected by its temperature, notably during charging and discharging. When overheated, batteries can reach extremely high temperatures of up to 500 degrees Celsius because of thermal runaway. The danger is that even thermal runaway in a single cell could engage a chain reaction with other cells, which could eventually lead to fires and loss of life and property. To prevent this and elongate their lifespan, lithium-ion batteries come equipped with a battery management system, or BMS. This board keeps track of important parameters like temperature, voltage, and current during charging and discharging of the battery. It's very useful in improving the safety and performance of lithium-ion batteries and does that by estimating the SOH and SOC, or state of charge, of the battery. So what's SOC? SOC is an indicator that represents the available charge stored in the battery compared to the full capacity charge of the battery. So the constant current, constant voltage, CCCV, is the most recommended charging convention. Following this charging cycle, which is shown on this slide, the system provides a constant current before dropping it when maximum charging voltage is reached to prevent overcharging of the battery cells. To find the C rate, the ratio at which a battery can be charged or discharged relative to its maximum capacity, one needs to know the total charge power as well as the total capacity of the battery. This way, C rate can be found using the formula shown on screen. While charging, the charger can monitor the battery conditions and adjust the charge current. Typically, ultra-fast charger may start the charging process at 10C, and as the battery approaches the normal operating voltage, the charger gradually reduces to 1C. However, this add-on of current at the beginning leads to an undesirable increase in the temperature of the battery. This is why the use of ultra-fast charger should be limited to when necessary. So in order to avoid this temperature increase by charging at faster rates, one way would be the battery swap. So this is done by physically removing the battery pack from the vehicle and replacing it with a freshly recharged battery pack. The depth of discharge is an important parameter that complements the SOC to indicate the health and performance of lithium-ion battery. It influences the charge cycles of a battery during its useful life. To elongate the battery, software controls are added to a BMS. These controls prevent the charging and discharging of a battery beyond certain limits. Now, how could we possibly maximize the life of lithium-ion batteries? The design of the electrodes in the lithium-ion battery can affect cell capacity and lifespan since chemical reactions take place there. This is why internal resistance at the electrodes should be reduced to decrease the generation of heat. The increase in efficiency of a lithium-ion battery has been linked to the size of its electrodes, as well as the material from which they are made. This key design factor allows the improvement of the overall conductivity and thermal performance of the battery. One could do that through coating, doping, or adding deposits such as gold, graphene, and zinc to the electrodes as they are being produced. Now let's discuss what happens in the afterlife of lithium-ion batteries. Lithium-ion batteries contain a wide variety of material which needs to be recycled for environmental and economic reasons. Zinc, lithium, copper, steel, plastic components, graphitic carbon, fiberglass, coolant, and even the BMS can be recuperated and reused in new batteries. The global market for the recycling of lithium-ion batteries is expected to hit $18 billion by 2030. At some point, all batteries must be recycled in order to avoid landfilling. However, it would be ideal to repurpose the lithium-ion batteries to take advantage of their full value before recycling them. Reusing is a great afterlife option so that we can maximize the economic value of the battery and minimize the environmental impacts. When the battery reaches the end of its useful life, it typically still possesses 70 to 80% of its original capacity. The most promising plan for end-of-life batteries is their integration into energy storage systems. These systems are very beneficial, providing backup power as well as a way to store generated renewable energy sources such as wind and solar for later use. Such use of end-of-life batteries could potentially extend the life of these batteries by 6 to 15 years or even more depending on the application. Such integrations were already implemented by General Motors and Toyota. In the image on screen, we can see how GM, one of the top PHEV manufacturers, are utilizing used Chevrolet batteries to store as well as supply energy to their facility and its adjacent parking in Michigan. This energy system can provide up to 4 hours of power in case of emergency. Now, in this next part, we will discuss the socio-economic facet and plug-in hybrid vehicles as well as their environmental impact. Electric vehicles in general have been pushed forward by governments all around the world to reduce their carbon footprint. This was done by many ways. One such way was through setting emission targets. For example, the European Union has set CO2 emission targets, which are planned to be fully implemented in 2021. These will bring penalty payments in the form of excess emissions premium for each car a manufacturer registers if the latter's fleet average CO2 emissions exceed the target. It is therefore in the manufacturer's interest to switch to the electrification of their fleet to decrease their emissions and avoid fines. Another way of encouraging the purchase of PHEV is through setting city access restrictions. This is done by imposing bans and even penalty taxes on users of ICE vehicles. Additionally, low emission zones have been defined in many cities in Europe. These zones do not forbid high emission vehicles from entering. However, charges are applicable and failure to pay may result in heavy penalties. Governments also encourage consumers to buy electric vehicles through financial incentives. This is done by providing cash subsidies, reducing taxes on electric vehicles while increasing or maintaining taxes on ICE vehicles. Additionally, more and more manufacturers have confirmed their willingness to switch to electric vehicles. This has led to PHEVs achieving price parity or even savings over internal combustion engine vehicles. Moreover, over the upcoming decade, we can expect electric vehicles to become low cost. This would mainly reflect the colossal drop in battery pack costs worldwide to $137 per kilowatt hour in 2020. This trend is set to continue and reach an average market value of 100 kilowatt hour as soon as 2023. Many consumers are attracted by the promise of reduced fossil fuel consumption and lower greenhouse gases brought up front by PHEVs. Indeed, electric vehicles play an important role in reducing greenhouse gas emissions. This is most notably noticed in city drivings, where speeds are not too high and the power for most of the travel is provided by the battery. However, even at high speeds, PHEVs still achieve lower GHG emissions than hybrid and conventional vehicles overall, as seen in the first chart on screen. Additionally, we must not forget the greenhouse gas emission intensity of electricity used to recharge batteries, which are taken into consideration during the charge depletion mode of travel. Charging on a grid with a mix of coal and oil as sources could add a lot to the GHG emissions of a PHEV. Therefore, a PHEV is generally only as green as the fuel source used to produce electricity to recharge the batteries. So now we're going to talk about the future technologies. The first one we're going to discuss is lithium air. Metal air batteries have been around for some time now. Zinc air buttons can be found in old watches or a hearing aid, for example. However, scaled up aluminum and lithium air chemistries are notably promising for the automotive and aerospace industries. The potential for high energy storage batteries, which are at the same time lightweight, makes this battery technology a promising one. Lithium air batteries could have a maximum theoretical specific energy almost 10 times more than lithium ion. One drawback would be the limited lifespan of battery due to the clogging of the pores with lithium salts after only a few tens of cycles. So possible solutions for this problem would be to either feed pure oxygen to the batteries or use nanoflakes to catalyze the formation of a thin layer of lithium peroxide on the electrodes. However, these solutions would still create safety hazards in automobiles, and lifespan would still be too short for the automotive industry. Another promising technology is nanotech. This type of technology makes use of particles that range from 1 to 100 nanometers. Research is being conducted to replace graphite and carbon metal composites electrodes by a nanochain electrode, which would allow extreme expansion. In the nanotech field, a new technology being tested is that of carbon nanotechnology, of which graphene is the most promising. Graphene has very interesting electrical properties, being a very thin semiconductor with high carrier mobility. Also, graphene is thermally conductive and is about 200 times stronger than steel. This battery technology would provide lighter and more robust batteries, which would last longer than what we can find on the market nowadays. It would also reduce the charging and discharging time and increase their capacity. The third technology we will mention today is that of lithium sulfur. This technology promises much better energy densities than lithium-ion batteries, as much as 7 times greater than lithium-ion batteries. Moreover, lithium sulfur batteries could be up to 7.5 times lighter than their lithium-ion equivalent. In addition, sulfur is a much cheaper material than cobalt or manganese, which are currently used in conventional batteries. However, some challenges are present in the development of this technology. First, sulfur is a poor conductor of electricity. Also, sulfur cathodes can expand 8 times more than cathodes used in conventional lithium-ion batteries. And additionally, this technology faces the problem of dendritic growth faced by many lithium-ion batteries, as seen in the second figure. The last battery technology we'll discuss today is the solid-state battery. This technology would basically be able to solve most problems that conventional lithium-ion batteries suffer from. So, solid-state electrolytes would replace flammable organic liquids. This technology fixes one of the most prominent safety concerns of lithium-ion batteries, which is fire. This would be thanks to the physical blocking of dendritic growth seen in the previous slide, which would then render the battery more resistant to short-circuiting and overheating. Many of the big automotive manufacturers are heavily investing in this technology due to its promising aspects. One challenge in this technology would be the expansion of the electrodes during charging, since it would be more difficult to manage in solid materials. Now I'll let Guillaume conclude.
Yes, so to conclude, manufacturers tend to play on the chemistries and materials in the batteries in order to produce the best possible battery in terms of performance, lifespan, power, and energy, while keeping costs as low as possible. But lithium-ion batteries are limited by their relatively short lifespan and risky nature. Many new technologies are currently being developed to fix the issues that today's lithium-ion batteries are facing. And these new batteries focus on solid-state, lithium-sulfur, lithium-air technologies. These advances will lead to safer, more robust, lighter, and more energy-dense batteries. And most of these technologies will probably see the light in the near future, even beyond the automotive industry. Thank you for your time, Doctor.
Thank you, Doctor.
Okay, thank you. To start with, can you go please to the first slide? So let me check the number of the slide.
I tried to put the page number, but it didn't show on every slide.
Yes, it's fine, no problem. Okay.
Okay.
So please go down with the slide. I will tell you where to stop. Okay, here please in the graph 15, slide 15.
Slide 15, yes.
Okay, Mark, can you please explain a little bit how we are comparing here the different types in terms of specific energy and specific power, and what we can conclude from the graph?
What do you mean how we are comparing? No, how it's put on the graph?
And here we are comparing in terms of specific energy versus specific power.
Yes, it's the specific power on the y-axis and specific energy on the x-axis. Okay. It's comparing different battery chemistries.
Okay.
And as you can see on the graph, ultracapacitors are the least. They are on the left side of the graph, so they have the lowest specific energy, but they are also the highest. So we can see that they have the highest specific power. So that's why, as said, they can be used as storage systems. We can see also that nickel batteries are average, and they have a not so high specific power and not so high specific energy. We can also see that lead acid batteries are the same. they have a high specific power, but not so much a high specific energy. But we can see the lithium ion batteries, which take a lot of place on this graph, since, as I discussed later on in the presentation, some lithium ion batteries can have high specific power and some can have also high specific energy.
Okay. Can you go down with the slides, please? Okay, can you stop here, please? Stop in the, yes. Slide 35.
Yes.
Okay. Can just please, Guillaume, explain for us the graph here?
Yes. So basically, this graph is the charging profile of the battery. So it shows the constant current, as Mark said, constant voltage charging convention. And by seeing the graph, you can see how the constant current starts to drop when the voltage attains a maximum value. And this is great because this prevents the overcharging of the battery cells, because in the long term, this can cause some strain on the batteries. So this charging cycle is the best, and it's the best way to do so to prevent the degradation of the battery cells, basically.
Okay, thank you. Can you go down, please? Okay, just concerning no, back down, please.
Down, يعني
Yes.
SOAP 40.
Concerning the socioeconomic evaluation. So based on this evaluation, what can we conclude? Mark.
So with this socio-economic study, we can conclude that electric vehicles are being more pushed forward, and it's, I think, in the advantage of consumers as well as manufacturers to decrease their emissions, CO2 emissions, and invest more in electrical vehicles. So I think in the near future, as the price of battery cells are dropping more and more, the cost of electrical vehicles will reduce even more, and the electric vehicles in general will be more popular in consumers, and I think we can see them more and more on the streets.
Okay. Guillaume, anything to add?
No, that's it. I think he said it all.
Okay. Okay, thank you.
Thank you very much for your time.
You're welcome. Bye.
Doctor, did you like the presentation
Yes,
overall?
nice. It's very nice. Yeah.
Thank you.
Out and